Welcome, everyone. So today we're going to have our international lecture series of with a special interesting group or like a technical committee of visualization and visual analysis group of China Society of Image and Graphics. Today we're going to have our fourth talk. So before we start, for our audience, if you are interested in have a discussion or like if you want to post some questions, you can either put in those the Bilibili site. We can collect the question and send it to our speaker, or like just join the WeChat group. I posted this code here, or like if this code is already expired, like or too many people join, you can just follow our WeChat, there's an ID, and then send your request. Okay, so today we have our great honor. We have invited Professor Eduard Gröller from Technical University of Vienna today give our talk. So let me give a brief introduction. Professor Eddie. Professor Eduard Gröller is a professor at the Institute of Visual Computing and Human-Centered Technology at Technology University of Vienna, where he is heading the research unit of computer graphics. Professor Eduard Gröller is the scientific department and the key research of the CSIG-VIS Research Center. This is a very also influential research center, and many people in China actually work with the center or like already know this one. So the center performs applied research in visualization, rendering, and visual analysis. So Professor Gröller is also the adjunct professor of computer science at the University of Bergen in Norway. So he covered a wide range of research interests, including computer graphics, visualization, and visual computing. So in the past years, he received many very important awards in visualization research. He became a fellow of Eurographics Association in 2009. And he is also the recipient of Eurographics 2015 Outstanding Technical Contribution Award. And 2 years ago in IEEE-VIS, he received the IEEE VGTC 2019 Technical Achievement Award. This is one of the most important research award for visualization researchers. So today he's gonna give us a lecture with the topic of visual analysis through spatial and the abstract data integration. So let's warmly welcome Professor Eduard Gröller. So let me forward my slides. Let me stop here. Okay.
Thank you, Xiaoru, for the very nice introduction. Can you hear me clearly?
Yes.
All right, I will try to follow the chat. So if something is going on and if I'm speaking too fast or something, just let me know. So thank you very much for this nice introduction, and also for inviting me to give this lecture. And as Xiaoru said, in the next hour or so, I will talk about visual analysis, and in an interesting area where spatial and abstract data are happening, and they are closely interacting, and then the analysis, they should be visualized together. So let me start with data visualization, which is the background of my research, and that's computer-supported interaction with visual representation of abstract data to amplify cognition. So this is a very well-known sort of definition. And the central key here is the data, and we are making images out of it and are interacting with this data. It is not for fun or for aesthetic reasons, but we would like to know more about the data. We would like to amplify our understanding, our cognition about that. And the importance of the data is reflected also in the traditional naming of subfields in our area. So there is an area which has been called volume visualization, volumetric data, like coming from the medical domain. Or there is flow visualization, which is visualizing vector fields or dynamical systems, data that is changing over time. And in many areas, and in physics, for example, this is guided by differential equations. So flow visualization is very important. And then there's a lot of abstract data available in databases, for example. And there have been an area which is called information visualization, which is producing this abstract view like scatter plots, where you are showing two attributes, and then each item in your database is a point here, and then you can look for clusters, for outliers. More recently, visual analytics came into existence, and this is a combined analysis where on the one hand, the data is so large or complicated, you need an automatic analysis, but you would like to have the human in the loop. The human expert should then make decisions, like in this flooding scenario. And then even more recently, visual data science is gaining in importance, where there's so much data now around because of the increasing number of sensors, of cameras, and other devices that are available. And the data is the source that is to be investigated, and visual techniques play a role here as well. And what we have seen in the last year, data is increasing in complexity. And why is that the case? I mean, this is also a well-known figure that the data can increase in volume. So from megabytes to exabytes, for example. Or the data veracity. So you can have certain or uncertain data. Usually in the real world, you have a certain amount of uncertainty. How can you handle that? And data velocity means, do you have static or real-time data? Nowadays, streaming approaches allow the capture of dynamic processes. So the data velocity is increasing. But in my talk today, I would like to concentrate on the data variety. So you don't have only one type of data, scalar data or vector data, but multimodal data, spatial data, abstract data. And that poses interesting challenges for the visualization domain. Let me shortly outline a few approaches, visualization approaches to cope with this increased data complexity. As the complexity of the data is increasing and data is the key of our investigation, we have to react to that. And we cannot fight complexity with complexity in the sense of making the visualizations more and more complex. So what approaches are out there? This is just a list of some of the interesting topics. The one is the comparative visualization. So you would like not only to take a look at one data set, but an entire ensemble. And in this case, the underlying data are point sets that are captured from a scanning, this figure here. And then you can have all kinds of reconstruction algorithm 1, 2, 3, and many. And how do these algorithms perform? And here you have a sort of a parallel coordinate plot that is showing you the performance of this algorithm at various interesting hotspots. Here you have these hotspots, and what we see basically here, this is an aggregated view where in color you are encoding how these algorithms agree on the reconstruction. And in those areas where you see red, this means the algorithms are producing deviating results. And that might be interesting for you to look which algorithm is right in a sense. So this is a comparative visualization. Quantitative visualization is another hot topic. In many cases, visualization produces qualitative results in the sense that you see patterns, that you see certain qualitative features, but in some cases, a quantitative analysis would be really helpful. And here's an example where with this brushing, you want to select a certain number of points. But in this case, the brush is making sure that you select 10% of the observed data. So when the next person is also selecting some part of the data in a quantitative way, you can be sure that you're selecting 10%, 15%, 20% of the data. And the second thing is here that the brush is not a circle in a way, but it is an ellipsoid, and the ellipsoid is adjusted to the underlying data. So this is a data-based quantitative visualization. Scalable visualization is increasing in importance. Nowadays, a phenomena can be captured on many different scales. But on which scale are you interacting and visualizing with the data? Here we see an example which is called DNA origami. So you take a large DNA strand and you are mixing it with so-called staple components. And these staple components make sure that this DNA strand is sticking together in certain positions, and you can basically generate arbitrary shapes like a small cube here. But then if you take a look at these data, you can take a look at individual atoms, at individual amino acids. You can show the strands by themselves, or even just the scaffold. And here you have a different representation of a different scale. So the scalable visualization is one way to cope with the complexity. And if you are interacting with a certain scale, this interaction has to be transferred to the lower and upper scales as well. And sometimes this is easily possible, and sometimes this poses problems. Then visual analytics, as I said, came into play. Here we see an example, spatial data, and at the same time you see annotations. Here you have a landscape, and flooding simulations are done. So if you have a breach at a river or an overflow of a river, you get this flooding. And here you have annotations, labels that tell you how is the flooding behavior at a certain spatial location. And it's necessary to calculate a lot of these simulations beforehand. So you have to do a lot of automatic calculations. But then it's the domain expert that is selecting one of these simulations or is interacting with specific parts in the data. So this is visual analytics, a combination of automatic and human-guided analysis. And here we see at the same time an example of linked and integrated views. A linked view means the data is so complex that you have several windows, and the windows show several different aspects of the data. Maybe sometimes you even see in a window an enlarged situation of a small item that you see in an overview window. And there's a subtle difference between linked and integrated views, and that will be a large topic of my talk as well. Linked view means you have windows side by side, and maybe they are linked through brushing, for example. But that's it. An integrated view is a more intricate combination of abstract and spatial data. Here we see anatomical structure. This is the hip area, and we see the skeleton. And at the same time, we have abstract data in the sense of an anatomical tree. And this tree is represented as a node link diagram. Here you see the links, and the node is enlarged, and you see them as a disk. And within the disk, you see a certain part of the structure. And is the child structure where you see one part of this. So this is an integrated view in the sense of that the spatial data and the abstract data are shown at the same place. In this case, it's the abstract space that is the guiding space, and you are using part of it, the nodes in the node link diagram, to give a glimpse into the anatomical view. And then next interesting thing is data in computational science. Computational science is about simulating phenomena, You don't have to do experiments anymore. You have differential equations, for example, and with that you can simulate and can investigate digitally your underlying phenomena. At the same time, you can have data, captured data. In this case, we see a virus, coronavirus, and this has been produced by the spin-off company Nanographics in our environment. And this is data that has been captured by a Chinese university, and this is a cryosection of a real coronavirus. But you see only a certain aspects of that, and you take that data and you combine it with the simulation. This is also called data assimilation. And then you can sort of put those together and you have data in computational science. The next step would be the visual data science, where you just take the data that you have gotten and you do the experiments, hypotheses, building, and so on with your data itself. And the last point or last subtopic I would like to point out is immersive analytics. This is a book that came out a couple of years ago, and it's about the use of engaging embodied analysis tools to support data understanding and decision making. So basically, a typical example would be an augmented reality, where you're moving around in a 3D scene. And in this scene, you get blended in maybe statistics information, maybe navigation information, pointers that show you in which direction you should move. And so this immersive analytics is an emerging discipline, and it combines the 3D spatial information with abstract information. And this is sort of a motivating example for what will follow now. And let me point out the special connection between spatial data and abstract data. And let's take an example from the medicine. Here, the blood vessel, this vessel tree is of interest. The bone are the context information that can be eliminated at some point in time. How am I showing this data? So the question is, it's about abstraction. What is important? Do I need to show the bones or can I do without? For surgical planning, the bones will be helpful. For other planning, maybe not. So the question is, how much abstraction can your spatial data sustain? And when you take this three-dimensional structure and you want to make a 2D image, there are various possibilities. So this would be, which is called curved planar reformation. Here you have an illustration how this works. You have this 3D structure of this one vessel, and in the projected reformation, you're just projecting the data, and then you get here the vessel. But here you see narrowing, and it's not clear, is this narrowing just in your image or is it also in your data? And this makes a big difference. The next thing would be that you're not doing projecting, but you are defining a surface where this blood vessel lies inside, and then you are straightening this surface. So after the straightening, the blood vessel is just wiggling around, but not in 3D anymore, but just in this surface. And then you see that this narrowing is actually part of the image generation. Or you can even abstract more, that you take the blood vessel and you stretch it. You stretch it that the blood vessel is just a line, and then the context is heavily distorted, but maybe that's not interesting. But for example, you see clearly the radius of the blood vessel, and maybe you see narrowing, and you see how long a stenosis would be. So this is a critical thing if you have spatial data. How much can you abstract of these data for the task that you want to solve? On the other hand, if you're thinking about abstract data, how much space does your abstract data need? And this is basically the take-home message of the talk, which I will underline with various examples now. So here we have a molecular structure, a cell, basically, and here you have the cell border, the membrane. This would be sort of a scientific visualization. Here you have labeling, which is very widespread and known. But if you have a very dense if you have a very dense scenery, where do you place these labels? How much space do they need? How large are they? In this case, this is automatically done and placed, and the label size also corresponds to the importance or prominence of the labeled structure. You can do a declarative navigation by assigning to these labels, to this abstract information, a semantic. And if you click on one of these labels, you are moving to that indicated structure. Or you can have your abstract data as a narrative, as a text. And in the text, you are describing some information about the data, and automatically from this abstract data, which is given here as a plain text or as a story, and narrative is generated, and you are moving through your data set. So here the question is, where's the space and how much space do you need for your abstract data? So this is the setting of the top. And in the following, I will explain 2 or 3 use cases that basically make up the PhD thesis of Thomas Ortner, who has finished this thesis just recently at the CSIG-VIS Research Center that was going on for a couple of years. And it's about the tight integration of visual analysis and 3D real-time rendering. Or in a different wording, you have abstract data, and then you have spatial data, and the spatial data should be available in a real-time setting. And how can you combine those? So first, let me make some special remark. So you have spatial relations. This is a tunnel. This will be the first use case that I will explain later in more detail. I will make now more general remarks. And here you have cracks in the tunnel wall, and you have to monitor and watch those. But you can also take a look at an individual crack that is defined by a 3D polyline. And at the same time, you have abstract data in a database, for example, where you have an ID for the cracks, then a length, how wide is the crack. Maybe you have several tunnels, a north and south tube, for example. Very important is the moisture. Is this a dry or moist or wet crack, for example? And the next information is about the exact position of the crack along the tunnel and along the cross section, and maybe also the orientation, which indicates if this crack is important or not. And if you do spatial queries, nowadays, if you have a digital model of the tunnel, you were capturing a lot of images, and the tunnel wall and the reconstructed image is maybe of lower quality, and you would like to go back to your original images. So if you're looking at the wall at a specific position, you would like to go back and take a look at the high resolution images, for example. Or you would like to create geometric and multivariate data. Here we see not the tunnel wall, but the cross section of the tunnel during drilling. And this is the reconstructed phase where the tunnel is constructed, and you are indicating or generating a new data, maybe where there are interfaces between rock types, and from that you make predictions that are helping you to define what's going on when you drill these tunnels. So in this case, information is derived and generated. So if you look at for such specific applications where you have a lot of spatial data, and this data shall be analyzed together with abstract data, for off-the-shelf tools, either it's infeasible, or you need cumbersome workarounds. You have to use several tools, and you have to move the data between that. So, but you can go for customized visualization solutions, which are integrating this multivariate and the geometric data. There are many cases domain specific, so you need a close interaction with the domain experts, and the creation can be challenging because you have to generate a software by yourself, and that can take quite some long time. So the idea of the PhD thesis was bottom up to investigate a couple of design studies and then derive certain guidelines concerning the data classification and task classification to find out if the special setting of having spatial and multivariate data requires specific approaches. And so the use cases are a tunnel crack analysis. I explained that before. The second one is a visibility aware urban planning. Let's see if I can explain this as well. Maybe I'm just explaining the first and third one. And here the situation is you want to build or construct a building at a specific site. How does this influence the surrounding? The economic infrastructure, the traffic, but also the visibility, for example, is a very important sightseeing hotspot impacted by this new building. So that would be, how can urban planning be supported by a spatial multivariate analysis? And the last use case would be a stratigraphic analysis of outcrop models. Here, geologists are taking outcrops, which are rock faces that are exposed because maybe of a river or a valley. And then you see different strata. And from that strata, you can derive certain aspects about the past. Were there any water, flooding going on, flow direction, and some biosignatures? Has there been life? And this is done also in the context of Mars expeditions to investigate rock formations there. So if you are thinking about design studies in visualization, as I said, there are two important components. It's the data and then it's the tasks. And those two independent factors define which visualization methods and interaction methods are available. So usually you abstract the general components of your data, then you think about which tasks and goals you would like to have, and then this specifies what methods you might take a look at. And there has been work in this area, like there's this standard book from Tamara Manzner, and that concerns the data set types. What data are you looking at? And she has been defining 5 data types from the table, networks and trees, fields. This is sort of the spatial data that we know from volume visualization, for example. Maybe you have a Cartesian grid, and in each position you have an absorption coefficient from a scanning procedure, or you have geometry where the items contain positions and other items like sets and lists and so on. So if you look at our the 3 studies, we have this multivariate data where items have attributes. We have seen this with this tunnel example. At the same time, we have also geometry where the items contain positions, but maybe even more. So it's not just like a point set that would fit into it. So it looks like this taxonomy of data is not fully complete with respect of this multivariate spatial analysis. And we would like to define a new one where we have multivariate geometric data. We have an attribute vector, which contains n abstract attributes, and then we have a geometric representation like before. But we would like to have this geometric representation a little bit more complicated, where it consists of positions from the R3, and we have more than just one. So we have several of those, maybe a mesh, a net of polygons and so on, and these positions are in R3. And so that would actually then an item in our multivariate geometric data would consist of a more complex geometric description and of the attribute vector. So when we look at these data types as defined by Manzner, I think we can add one more data type with this multivariate geometry where we have items as well, and then a shape. So not just positions, but a combination and positions with a certain relationship. and various abstract attributes. And so that's what is better suited to describe the data for our use cases. And in the why, this would be the tasks that we have. But for multivariate geometric data, these tasks can have a geometric aspect. So when I'm concentrating on the geometry, and that is, as Mansner explained, shape understanding. But the shape understanding can be that the primitives, that the positions that we are looking at amount to a certain shape. Like here, I mean, here we have an abstract representation and here a selection window. This is selecting certain positions in the brain. And these positions make up a shape by itself. And we would like to understand this shape. So this is one thing. The other thing is that each item by itself has a certain shape. And maybe we would like to compare adjacent shape. Do they compare concerning their length or their attributes and so on? So there are these geometric tasks. And this analysis of shapes, when we have also abstract data, has been analyzed in other taxonomies here by Oelze and al., where they are talking about linked representations. And so you have several linked views, and maybe you have an abstract representation, and here you have a brush. You see these two rectangles, and this is a smooth brush. You are fully selecting the data inside here, and these are only partially selected with a certain degree. And a feature localization means you are interacting with an abstract view, and then you're looking at the spatial view. Where do these data points happen with these specific attributes? Multivariate analysis is just analysis in the attribute view. You are staying in the abstract domain, and maybe you are changing, you're selecting in one scatter plot specific attributes, and then you're switching to another scatter plot. The local investigation would then be in the spatial domain where you are interacting with the geometry. And interacting with the geometry, maybe you are changing the viewpoint and look at the data from a different side, something like that. So this is if you have attribute data and how you can interact. Still other taxonomies on visual occlusion handling from Elmquist and others is talking about visual perception tasks for shapes. And the one is discovery. Where is a specific shape? And the other one would be access. How can I closely look at my data? And maybe, as I mentioned before, in the comparative visualization, what is the spatial relation between the data? So here we have other tasks where this one is sort of defining the interaction with abstract attribute views. Here, but the shape is not so much of interest here, maybe spatial locations. And here the shape is in the center, where attributes or abstract attributes do not play such a large role. And we would like to integrate these taxonomies together with what we know from Mansner and make it applicable to our use cases. So in the Mansner book, we have multivariate geometric tasks. You can analyze, you can search, you can query, and basically they are subdivided in the consume area and in the produce. Here you are using the data to discover or present and so on, or you produce it, you annotate it, you generate labels, or you derive further data than you are looking at. And if you take the abstract analysis tasks and try to tie it in, then we see that the feature localization is reflected here. The local investigation can be the browse here. And also the second taxonomy of Elmquist fits nicely into here. Access can be sort of identify spatial relation can be compare, and discovery can be locate. Multivariate analysis is, we leave this away, as this is dealing with abstract views, and you are interacting with various abstract views. Here we are interested in this interplay between spatial and abstract data. And the one thing is consume, and that will be in the first use case. And in the produce section, which we will see in the second and third use case, especially the annotate and the derive task is important. We derive in the urban planning visibility information, quantitative values, quantitative visualization, or in the geology use case, we are annotating the data. So the next would be, so we have thought about how to tie in this data into data taxonomy and also task taxonomies. The next thing is, how about visualization? What would be good approaches to visualize these multivariate geometric data? There have been guidelines when to use coordinated multiple views. So if a single view is a cognitive overload, the data is too complicated, you use faceted representations. So you're using multiple views, and these views share certain things together. Maybe they show the same data, maybe they have the same encoding. And if there's a large variety in the data, this would be a good indication to have several views which show different aspects of the data or facets of the data, and they are coordinated. How are they coordinated? In another survey by Kehrer and Hauser and by the book by Manzner, it's brushing and linking. Brushing and linking means I'm interactively selecting in one window a certain part of the data and items. It immediately, in all the other windows, I see corresponding reactions. The same data is selected, for example. So if you have spatial and attribute views, this brushing and linking allows you to keep a mental model if you are switching from the spatial to the abstract view. And this correlation is also supported by having a shared encoding. You're using the same color for the same type of data, for example. Or you are showing at least partially the same data in separate views, and this allows you to coordinate that. So here we see an example of linking and brushing. Like in the attribute view, you are selecting a certain part of the data, and immediately the same data is highlighted in the geometric view. And then you can move around. And here we have two types of selection. In red, the selected data, which is shown here in red as well. In yellow, we have the context, which is the not selected one. And we have shortly seen also, which is called peak selection. You're peaking on the data. You are not selecting the data, just hovering the pointer on the data, and then it is shown in blue. But linking and brushing here is not sufficient by itself. If you select all horizontal cracks with a certain length, then in the 3D view, actually certain of the selected data is not shown or is partially shown. You see only a part of the data, and the camera frustum is only capturing part of it. So this means that you would need a more integrated interaction where the selection leads to a viewpoint selection, for example. And so a tight integration of geometric and attribute views is necessary, where you don't do only just linking and brushing. The integration has to go beyond that. So semantically, what you do in the attribute view leads to a more complex interaction and rendering in the geometric view. So the idea would be to prevent multivariate geometric tasks from failing by not showing all the relevant information because the data is outside or is occluded. In a 3D rendering, occlusion is an important problem. The overall goal will be to provide the users with a continuous analysis experience where it's not necessary to go then explicitly to the 3D view and have a lot of manual viewpoint tuning, for example. And so this brings us back to these scenarios. And then the first one, we will take a look at the tunnel crack system and the tunnel crack analysis. So if you build a tunnel, then, you have to, there are three phases. A tunnel is planned, then it is constructed, and then it is maintained. And this use case concerns the maintenance. And the contribution of this design study is twofold. The first one is a specific visualization system for tunnel crack maintenance and supervision. And based on this, to get a more refined, tighter integration between attribute and geometric visualization. Here down in this part, we see sort of the mirror layer where the attribute and the geometric visualization are in a very simple way linked with each other. So this would be linking and brushing. You select something in one view and you select it in the other view, or you do this peak selection by hovering, or the connection is simply you're mirroring. Temperature in one view is in red, it is in red in the other view as well. But it would be more interesting to have this more refined integration layer. And the second outcome of this design study is here some general approaches that have been abstracted from this design study. This basically concerns the consume type of tasks that you have, and that means locating, browsing, identifying, and comparing. So what's going on in the tunnel maintenance? Well, in the past, people were manually going through the tunnel, were inspecting, maybe were taking pictures. So there was a physical inspection with taking notes and pictures. This led to lockdowns for several days, for example. It was difficult to manage the data. Maybe it was not digitally available and so on. So there has been then a trend towards a virtual inspection of the 3D surface by capturing the tunnel data and then analyzing it digitally. And so the data acquisition is done on a variety of platforms. This is mounted on a track, for example, where high resolution cameras are involved, and also a laser scanner to capture the distance, for example. Maybe in a street tunnel, you have a different setup. There's been a company involved that is sort of capturing this data, and there are various special purpose setups with lighting situation to capture the data. After the data, some pre-processing is done and a 3D model of the tunnel is reconstructed, and there have been at least semi-automatic approaches to detect the cracks on the imaging data. And here we see such a tunnel which consists of 2 tubes, and I think there's about more than 1,000 cracks with abstract attributes, and the tunnels are represented in polylines. So we have the tunnel with geometric polylines by itself, and then we have, as already mentioned, these attributes, length, width, the moisture schedule, which is really important to find out if water is entering in the tunnel and is damaging the tunnel, and a repair operation is necessary. And the SV and B are the coordinates where this is located. SV is the coordinate along the tunnel central line, and B would be an angle along the cross section. With the current approach, the shortcomings, as I mentioned, have been that the geometric and the multivariate data is investigated separately. There have been a lot of static reports that have been available. There was not an integrated workflow, and it was cumbersome to export the data from one format to the other and to relate the data to each other. So that was a manual process. And the task analysis with domain experts led to some domain-specific tasks like finding cracks with anomalous attributes. That can be also the moisture distribution. This is interesting. Maybe there's some water entering the tunnel. And what is a critical section? A tunnel is usually subdivided along the length in various sections. What is a critical one? It can be the density of cracks. When you have too many cracks in an area, that might be an issue. Maybe there are intersecting cracks and then high moisture is showing up there. And is there even between adjacent tunnel tubes, is there moisture transfer? So this might be that there is a position in the mountain that is bad for both tunnels. And the design goals following from these tasks is to localize single and several tasks, and also to find out based on abstract attributes, where are the cracks located that have these attribute values, and in the abstract view, are there clusters or outliers? And basically, the idea would be to have a digital system and a tight integration of a geometric and attribute views. And this led to such a multi-view system, where on the one hand, we have a 3D view, and where the cracks are color-coded. If they are brushed in red, in blue, peak brushed, that means you are hovering with the mouse in an attribute view, for example, and in yellow, this is the context. On the right side, there are 3 attribute views. The one view is a scatter plot, and in this scatter plot, you can show 2 attributes, orientation compared to length. You can select other attributes as well. The domain experts are less used to parallel coordinate views. Here you see all the attributes shown on the abstract attributes on individual axes. And this is an interesting representation, the third abstract view, where vertically it's subdivided to show each tunnel separately. And then along the horizontal axis, you have the tunnel encoding. This is the start of the tunnel. This is the end of the tunnel. And each tunnel, according to the tunnel length, is subdivided in sections. These sections also correspond to how the tunnel has been produced. And for each of these cells or each section, you have then a histogram, and the histogram tells you a distribution of the crack according to the most interesting abstract attribute. Is it dry? Is it moist? Or is it wet? So this would be the setup, and linking and brushing has been included in the representation. Here you see, you have been seeing the interaction behavior. And if you select something, you immediately see in the other windows what's going on. But linking and brushing by itself is not sufficient. As I explained before, what you are selecting here is only partially visible. So for the localization and more integrated, not just mirroring the selection process, leads to a more integrated view. And this is for the localization. And the localization can affect a single crack, or it can affect multiple cracks. For a single crack, this means I'm selecting one individual one, like I'm highlighting only one single crack, and then automatically a characteristic viewpoint is selected. From an overview point, so that I know where this crack is located, I'm automatically calculating this characteristic viewpoint on a sphere that is centered around the crack and so on. And then we have a localization transition to get a close-up view. So the idea would be not to lose orientation. For multiple cracks, if you're selecting several cracks, the strategy is the same, but here the transition is moving to an overview position where all the cracks are then visible. So again, here you can have all kinds of transitions. These are very specific now to this scenario, but one can think of in other scenarios like the urban planning, in different scenarios, how this transition could be user-defined or domain-defined. The second step is in the geometric rendering of this attribute, in the sense of in the selection process, you have a focus and context. In this case, the rendering would mean that you are not changing, you're not changing the color, but you're changing the glow. So the selected information has a highlight around it. And this means that you immediately are recognizing what's going on. And by not changing the color, for example, you can keep the color channel free to encode something else. So this would be in the geometric rendering one task. Another one would be occlusion handling. So in the 3D setup and with these tunnels, you also have occlusion, and you could apply a virtual X-ray technique where the selected cracks, but they are occluded, are shining through. So they are shining through semi-transparently, and they have a larger glow. And you could have other approaches how to handle occlusion. You could do cutaways, for example, but that was not so much appreciated by the domain experts. So another way in this geometric rendering is how to handle visual clutter. I mean, if you have thousands of cracks and the view is in such a way that they are strongly overlapping, what are you doing? And in this case here, one strategy was to abstract the shape in a way. So a crack is reduced to just a point, and you're reducing, you neglect the identifier. You cannot see a specific shape of the crack anymore, but you know where it is located. So let's take a look here. And if you're zooming out and this information is getting too much crowded, you're reducing every crack to a dot, and this gives you sort of a distribution of that. We know such strategies from cartographic projections, where it's called generalization. If you are moving to a higher level, but you still would like to show important information like highways, for example. And the last part of this integrated interaction between abstract and geometric view is a similarity-based analysis. So you have an abstract view, you're selecting a focus point, and then you're defining what would be cracks close by. There you have to define a distance metric. What does it mean that two cracks are similar? It could be similarities defined by their spatial location, by their orientation, or something like that. So here you can define all kinds of metrics. This is important how you define that. And then you do a focal point update. Sometimes you are changing your focal point. You are concentrating maybe on a different orientation. And then you would like to see all those cracks that have a similar orientation. So this would be a similarity-based analysis. And so there have been several design sessions with the domain experts. I don't want to go too much into that. There were informal feedback sessions with 4 experts from tunnel maintenance and tunnel monitoring, but also in a different setting, infrastructure planning in an urban setting. Experts were asked if they can think of that this functionality might be generalizable to their setting as well, disaster management and so on. So the animated localization was considered to be very helpful, and the domain expert appreciated that. And the occlusion handling is great for orientation, but during the inspection, it might be distracting. So because if some crack is shining through it, it's on the other tunnel wall. In the overview representation, that's interesting, but not in the detail inspection. and useful in an urban scenario. This occlusion handling, where you have many buildings that are occluding structure behind, might be interesting. And the similarity-based analysis is useful in the tunnel cases, and in the urban setting, the domain experts were not so sure about it. But when we come back for the second contribution for the methodological framework, well, we had this very simple linking and brushing, which we consider this coordination layer between the faceted representation in several views. But it was in the integration layer where these specific interactions have been investigated. And the guided navigation was about localizing single cracks or several cracks, and the geometric rendering. In this case, for the tunnel, it was this glow rendering, occlusion handling with shining through, X-ray rendering, and visual abstraction, reducing cracks to dots. And with the similarity-based analysis is how to define the metric and how can I place the focus point. And so this is sort of derived from this analysis. And if you go beyond this tunnel design study, you can ask in a different setting, what are characteristic viewpoints? How do I get an overview viewpoint? How to transition? And in a different setting, this might be different, but the general strategy might be there as well. Also, how do I highlight or low light specific small parts of the data in the 3D setting? Are there occlusions, or is there too much information? How can I reduce the information to the most important one, or which visual abstractions are helpful? In the domain of immersive analytics or virtual reality, there's also the aspect of reduced reality. So you're taking away details because that's distracting from your analysis. And in the similarity analysis, in a different scenario, what is the distance between buildings, for example, not only between cracks as in our use case, and how can I specify focus points and update those? So in conclusion, we came up with an integrated solution for tunnel crack analysis that is combining the geometric and attribute visualizations. And there was this generalization where certain approaches were derived, which can be interesting in other scenarios as well. So let me come now to the I think I will go to the third use case. And maybe if I have time at the end, I will talk about the urban planning use case, because this digital outcrop analysis is more recent. So let me move to this analysis. And here, what is it about? It's a digital outcrop analysis. So geologists are looking at rock formations, and from these rock formations, they derive a certain information about the past. And when we go back in our task analysis, this analysis is more in the produce region, and we are annotating spatial data that has been captured digitally. The urban planning scenario would be in this derive setting. So why are these outcrop models so interesting? In the past, they have been done more in physical by geologists going into the field and looking into the rocks. But if you have a capture of the rock face and images, you get a digital model. It's a DOM, a digital outcrop model, and then you can analyze. In a different setting, like if you have generated the data from Mars, and there are Mars expedition, like the NASA Perseverance expedition, or the upcoming expedition of ESA on ExoMars. These expeditions are capturing geologic structures, and the idea would be to look for biosignatures. So if you look at these rock formations over a very long time, they might contain biosignatures or other indications of flow patterns. Was there any air or water flow? And from that, you can derive certain knowledge. The idea would be to have these outcrop models in a digital way. On Earth, you could do this in person, but like on Mars, you rely on these digital outcrop models. And this is a terrestrial outcrop from Utah. And here, maybe there's a river and a canyon, and then you have these outcrops. And these outcrops exposes different layers, and they are called stratum or strata layers. And they are delineated, and how thick they are, what color they have, what the grain size of the material is very helpful. And the next would be sort of a digital model from Mars. And if you compare that with this outcrop in Utah, you see why this terrestrial scenery has been used as an example. And this is a Martian outcrop model. And here we see a digital outcrop model has been captured by stereographic capturing and cameras. And you see the geometric model, you see the 3D structures, you see the layers. But the next step would then be that, but this is not from Mars, but this is from Utah. But the next step would be to do a geologic interpretation. And the geologic interpretation means that you are defining these units, these contacts. Contacts are the separation of adjacent layers. And this is done in a hierarchical way. I mean, some of these layers are more prominent than others. And within these so-called units, you have bed sets. So this is sedimentary layering that is happening over very long times. And basically, these are smaller interfaces, not so prominent. And basically, you have a hierarchical subdivision of these rock faces. The next interesting feature would be so-called crossbeds. And these crossbeds are here, these white lines. And from these white lines, you are also capturing the orientation. You're defining these discs. These are so-called dip and strike arrows that are pointing sort of in a certain direction. In which direction is this crossbed pointing? And these crossbeds are coming from the lee side of flows. So where there's not the flow is going over this, and then these small interfaces build up. And they are an indication in which direction the flow has been. And so they are very interesting. Has there been a flow, and in which direction that has happened? Based on these 3D data, then in a manual way, the geologists are generating a sedimentary log. And they are capturing here a line through this rock face. Between these beds, there's the distance is interesting, but as this is not happening orthogonally, and then you have apparent thickness, and you were interested in the true thickness. But basically, this one line through your rock formation is mapped to the vertical line. In the horizontal line, you are showing the grain sizes in a logarithmic scale. That the type of grain sizes and how prevalent they are is very important. And then in color, you show what type of rock is given here. You have all kinds of other annotations, glyphs that are giving indication on the setup of the rock formations here. And this is another interesting part. This is a glyph, that's a rose diagram, and that is indicating all these arrows in a stratum. you're combining the direction information that you have in a stratum. Each crossbed is delivering one arrow, and then you have this rows diagram, and that tells you in which direction sort of the flow in the stratum has been. So this has been going more in the easternward direction, and in this layer that was more like a northeasterly direction. This is manually illustrated, and there's no accepted standard in this domain. And so the basic data was from this Utah site where 4 outcrops have been investigated along this canyon, and then they produced these manual sedimentary logs. So these were the four logs, and they were manually generated. So the next step would be to come up with a correlation panel. These logs are not considered by themselves. So this is a very complicated scenery, and I'm not explaining all the details. But what is really interesting is that these 4 logs are taken, and then they are correlated. And correlation, not in the mathematical sense, but the geologist is identifying a specific layer. And then in one log, he's specifying the same layer in the next log, and they are combining those. And when you have a dashed line, this means you're not so sure. You try to sort of interpolate the situation in between the logs. You only have the specific information at a few places. And maybe you have a very specific layer. In this case, this was a fossil layer where you had certain fossils, and this has been the leveling layer. So you align vertically all these logs so that they correspond to this layer. And also how you align the logs next to each other depends on maybe the geographic situation or some other situation. The shortcomings of this very manual process is they are illustrated manually. There's no standard. This is very time consuming. And if you later on have to adapt it or extend, this is cumbersome. There are no interpretation tools that directly support this logging and log drawing. So you have, again, multiple tools, and you end up with static representations. And later on, if your hypotheses have to be adjusted, it's very cumbersome because you have to do it all over again. You cannot have an interactive tool. So the goal of this study here was to have an interactive correlation panel that is supporting 3D logging, a tool that is helping these to generate these logs in a simplified way. This is a manual representation, and this would be a simplified one that we were aiming at in the tool. And here we see an example that was then generated with the analysis tool. And then the next would be then having an interactive correlation panel where these logs can be correlated with each other. And the evaluation was done with a use case. Can I replicate results that have been manually generated, and the design validation by getting qualitative feedback of users? I'm not going into much details here. And in the task analysis, the one is create a log, one specific log for one specific outcrop, which means the strata have to be defined. Then for each strata, what rock types are happening there, and then the crossbeds to get these flow information for biosignatures. The second task is then to correlate these logs with each other, how to find similar strata, and then connecting these together. And the third one is sort of not so interesting from a scientific point of view for visualization. It's the vertical alignment and export, so that later on the domain experts still would like to have the information digitally as SVG graphics so that they can handle it with their own tools. And now let's take a look at these, how the system looked like. This is again this setup with a 3D representation. and then a representation for the correlation panel. This is the interesting one. And then some further views here, for example, to define what rock types are used here. So the task 1 to create a log is you can identify individual contacts, delineations of bed sets. You're marking them, you can edit them. You don't have to select them in succession because the layering defines ordering anyway, and this corresponds also to the temporal ordering how this has been generated. And when you are then finished, you get then an empty log, and then the next step would be that you are specifying for each log what rock types are given here and further information here. So you're selecting one of these layers. You see also the layer in the rock face. You can go back and interact with it. The dashed line here again indicate uncertainty. And here in this fast advance, you see how these rock types are assigned here. Then the next step would be for each stratum. The second thing part is assigning crossbeds. You're identifying these crossbeds, and for each crossbeds, you get this dip and strike orientation, and based on that, you are generating these rose diagrams. The next task, the task T2, would be to create these correlations. And the correlations means that in this correlation panel, you have zoom and panning. You can move between the individual logs, and then you can, here we see the zooming. You identify a stratum and in the other log as well, and then you're connecting those. You can connect various of these pieces. If it's a solid line, you're quite sure about it. Dashed line means it's uncertain. You could also define a leveling surface. You take this one, the top maybe, and you align all the logs according to this leveling surface. The distance might correspond to the distance between the logs. Also the arrangement of the logs, maybe here the positions of the logs in the geographic context are taken. So this is T2, the creating the correlations. And the use case and design validation, there was sort of anecdotal feedback where the domain experts were rather happy about that the manual generation of these logs would take days or several days. That has been reduced to hours. Only a few experts have been asked here. It's not something like in information visualization where you can ask 20 or 50 scientists, only a few of those. And they were mentioning certain aspects that they like. So the speed up, that is really a big advantage. And also being able to correlate and change the arrangement interactively and going back to a previous design phase was considered helpful. And also maybe in the future, experts can present their data with such an interactive correlation panel. And if new information becomes available or an interpretation has to be adjusted because of new knowledge, this can be done in this interactive way and not with static depictions which you have to start all over again. So for the geologic study here, the idea was to translate a static illustration into a data-driven dynamic one. And this digital outcrop model handling in a correlation panel was accelerating the analysis quite fast, from 10 to 20 times. So this is very fast. And so more advanced visualization techniques have been introduced to the domain of sedimentology and stratigraphic analysis, and also vice versa. So if you look at the visualization literature, there have been some works around geologic visualization, but not in these specific contests. There have been work in investigating drill holes, for example, which in our case would be sort of these outcrop positions. It's a similar, but still a different setting. So in total, what I have shown here is a tight integration of geometric and attribute views, where there's still a lot to be done in to have a bridge between the real-time rendering and the visual analysis. And we have identified a few gaps in the data taxonomy, also in the tax in the task taxonomy. And in our use cases, we identified especially 6 tasks. I didn't talk about the urban planning scenario, but I have given a literature reference, so if you're interested in that. And then we derived this methodology that gives some hints where in this integrated representation or combination between abstract and spatial data, additional research can be done. And it was a bottom-up methodology, first looking at various design studies and identifying commonalities and refine these visualization guidelines. So with this, I would rather come slowly to an end of my presentation. Let me take a look. Let me see if I come to the finishing slide. So this is a busy slide, and I will not go through all these individual aspects. These are topics, for some of them I talked about, that might be interesting for spatial and abstract data integration. I wanna stop with showing a video how to illustrate a virus that was sort of in this area of data science and computational science. I've shown this image at the beginning. At a Chinese university provided cryosection data from a frozen virus from a coronavirus. And our spin-off company has then used this for modeling and combining that and to illustrate that. And let me show this video, but I think I will share this so that you can hear also the sound. So let me see. Okay. Let's take a look at this video. So with this, I would like to come on into my presentation. There are references. I will make the slides available. But basically, what you should take away from this presentation is that there's the integration of spatial and abstract data is a very interesting topic. There are many open issues and challenges in this domain. And it's this interplay between the spatial data and the abstract data. How can you combine those? And how much abstraction can your spatial data sustain so that you can still show what you need for fulfilling your goals? And on the other hand, how much space does your abstract data need? So thank you very much for your attention, and I'm open for questions.
Okay, thank you very much for this very wonderful talk. They are rich of information. So we hear a few really examples that's like interconnect visualization with some like research work or engineering work. We can see how visual analytics can really be used to help some traditional work, like doing the tunneling. So we receive quite many questions so far. So this is the people from the Bilibili or like people from the audience group. So let's see. First question. That's about, they ask how the detection position of the device on the tunnel surface cracks affect visualization and analysis results. So asking about the device position and how related to the result, and also across the level of detection of surface cracks seems a kind of data abstraction. That's the first question.
Yeah, thank you. In this case, the data selection is been done by a participating company that is an expert in that, and the capture is done on a sub-millimeter with a sub-millimeter precision. And as I said, they have a semi-automatic crack detection procedure, which we are not so much involved at. They are going and looking at the data, and I think they're making sure the false positives are not the issue. It might be the false negatives, so that you're overlooking a big crack. But at the moment for the street tunnels, that's done on a sub-millimeter resolution where they are capturing the data.
Okay, thanks for the next. Actually, there are a few questions they're asking about the relationship between visual analytics and VR. So let me combine them together. So the audience asking like if you can comment on the spatial and the abstract data integrated in VR, and if this is the future, or like what kind of a scenario in visual analytics could be used VR or like AR. And if it seems that person is also working on this, so he asked like what kind of research questions they can ask.
Yeah, this is a very interesting question, and there has been actually a very long relation between virtual reality and scientific visualization. For example, long time ago, there was a virtual wind tunnel where you were inside a wind tunnel, and you could investigate how the flow is going around a car or so, and you could inspect the 3D phenomenon in situ. And then for quite some time, less was going on in this direction. And with this immersive analytics that I was talking about, this is now coming back. And I think this will be especially interesting for augmented reality, where you are having an in situ situation, a 3D spatial domain where you are moving, and you would like to get an overlay, which you nowadays already have in a car. In the luxury cars, you have a display that is projected on your windshield, for example. And this overlay of this abstract information on the 3D space is very interesting. And here you have a lot of aspects that are not yet solved. I mean, how if you have the 3D scene is already complex enough, how can you do occlusion handling that you are reducing details from the real scene? And how are you aggregating the information in an abstract way. If you are in a city model, for example, but you would like to see data aggregated in a statistic way, what's going on in a certain direction, how many buildings, what's the building density in a certain direction. You don't see it in real life, but you can aggregate that on the statistics. So this, I think this term immersive analytics might help where it's not only for augmented and virtual reality, but sure, these devices might be really helpful so that you are immersed in a real 3D space, and then which of these visualization techniques are then applicable. You have to project them on band surfaces, for example. Which interaction is possible? In InfoVis, you usually have 2D charts. How does this translate to this setting? So I think with immersive analytics, that's a good connection between visual analytics and virtual reality, and especially augmented reality.
Okay. Yeah, it seems now like a lot of people, they kind of really care about those VR, AR, especially in recent few months, some bigger company, they're in high favor of this so-called meta universe. So whatever. So maybe like there's a few more like business interest in AR or VR. Yeah. So maybe in from the visualization side, yeah, there's quite a lot of things we can do. There's also some people asking like, let me see, asking about how to like effectively represent the spatial data, either like other than volume data set, like what kind of, so this question is kind of vague a little bit. Yeah.
Yeah, and therefore it's good that it is vague, because my answer will also be vague. It depends on, it really depends on the tasks that you would like to fulfill, and also on how much processing power you have available. So if you're interested in ensembles, for example, so then maybe you go for an aggregated representation. Maybe there's the data is so much that you can only stream the data. You don't have all the data available in your computer, and that requires all kinds of different strategies. So I think this is highly dependent on the setup that you have. In this urban planning or in a flooding scenario, for example, maybe you are just interested in the ground planes of the buildings, not how they look like in the 5th floor. So you can abstract that away. But this is, I think, highly dependent. And if a volumetric representation is necessary, that is also, what tasks you would like to have. In a geologic scenario, where in archaeology, for example, in digital archaeology, volumetric representation is helpful because it tells you where are the artifacts in the ground, for example. In this tunnel analysis, surfaces are sufficient. So.
Okay. So maybe like I can, this is the questions I received so far. Oh, there's one more coming. The new question asking about that graphs are often used to abstract the relationships among spatial data. So what are the next candidate for abstract visual representations? And is there any general to select or design an abstract representation? So asking about like what kind of a new way to represent the spatial data.
There are general patterns, for example, like normalization, like aligning, well, you can put them next to each other, juxtapose them, superimpose them, or calculate statistical values and encode variances in that. Or one strategy is unfolding. I have shown these blood vessels, and you are aligning, so a line up in a way. You take the blood vessel and make a line out of them. So that would be a straightening along a line. You could make a flattening along a surface. Or in this outcrop model, you could see these strata, and these lines were sort of in 3D, an arbitrary line, but that was then in the log representation, the vertical axis. So I think there are general patterns that you can use, and like aligning, normalization. Then another strategy would be how to handle visualization, occlusion management, making it transparent, cutouts, what you do in illustrations. So there are various strategies. I couldn't say what would be a new strategy. I think a new strategy will be that the sceneries will be very dense. Imagine that you are in a molecule. A molecule is very dense, and maybe you don't even see an orientation. How can you sparsify that? So if you have a situation which is utterly has utterly detail, how can you selectively get rid of these detail? Not to show what you're interested in, but thinking about what not to show in a way, and that has impact on navigation and also on the representation.
Okay, great, thank you. Let me also share this this slide. So if someone, our audience from Bilibili, if you want to participate in a discussion or like ask more questions, you can scan this QR code and join the group asking more questions. We could wait 1 or 2 minutes more if some other people want to raise new questions. Maybe I have one question for myself. So here, like Eddie, I see like you collaborate with a very different of people, like they are from like really different from other different research domain. So maybe you can like share some experience how you get approached or you approach to other people, like how our visualization people can collaborate with some traditional research group or like people from other engineer domain. Is there any some experience you can share with our audience?
Well, this is a difficult task, the VIA-VIS is a public-private partnership. So whenever they do a research project, 50% of the money is coming from the government and 50% is coming from the participating company partner. So this means that a research project done with VIA-VIS is rather cheap for the company. I mean, which reduces the risk for the company. So this is a big advantage. So if there are a few projects where the company is paying fully for the research project, and then it's very difficult to acquire. And the VIA-VIS already exists for 20 years now. And some of these collaborations take really years to develop a joint understanding, to get the trust of these people. And from the visualization side, that you learn to understand what are their problems. I mean, they are not so much interested in your fancy visualization techniques. They would like to solve their own problems. And part of the problems they have nothing to do with science. It's about data management and data handling. And they are not computer scientists, but would need somebody for data management, exchange of, and you also have to provide that to them. And if over the years, a certain month, a certain working relationship has evolved, it's very good to keep a tight integration. So having regular meetings and workshops, not at the beginning to define the problem, and then after a year or half a year coming back with a solution, because it takes some time to understand their language and what they really need. And so I think this is a process that takes quite some time to evolve.
Okay, great. So there's more people. Is there like any other people want to ask some further questions? Actually, you can search Eddie's email from the internet, very easy to find out. And either you can send us information we can forward to Eddie, or like you can directly send the email to Eddie. Maybe next year, like when we have a chance, maybe Eddie can join us in CSIG-VIS or some other events. We